Yeah, so thank you very much for the invitation, and it was nice getting to know you a little bit. So don't hesitate to interact with me during the talk. It's nice that we interact. So I'm going to speak about continuous Bose-Einstein condensation and superradiant clocks. And that's in the field of ultracold quantum sensing. And let's introduce this a little bit with the example of a clock, which is a sensor that senses the flow of time. So if you lived like 200 years ago, and the king ordered you to build him the best clock in the world, then you probably used just a pendulum as the frequency reference for your clock. And pendula are not really that great as references, because if you build a second pendulum, you can try as hard as you may. This is a macroscopic human-made object. You cannot reproduce it exactly, so the second pendulum swings with a slightly different frequency. And therefore, then one day the king will be late for his appointment, and you are in trouble. Yeah. Luckily, we do live in a quantum world, and the quantized energy levels of atoms provide us with an ideal frequency reference, namely the frequency of the electromagnetic radiation that you need to drive transitions between the levels in the atom. And an atom is made by nature. It's just made by the laws of nature. So all atoms of a specific isotope are identical, as far as we know. And if we want to build a clock, we just need to read out this transition frequency as well as we can. And to build a really good clock, we choose a transition with a high frequency and a narrow line width, with the two levels not influenced by anything like magnetic fields or such. So an optical transition with millihertz line width is great. And we want to get a lot of signal from our clock. That means we should use many atoms, but these atoms, they shouldn't touch each other, because if they would, these energy levels would shift around. So we want a gas of atoms. Now, in a gas, typically at room temperature, these atoms move around with hundreds of meters per second velocity, which produces a lot of Doppler shifts. Also, you can't observe the transition for a long time, which is bad, yeah, for a transform limit. So you need to cool your atoms, ideally to stand still, and to get rid of this Doppler effect. And for that, you need a very good fridge, but not a normal fridge, like you have it for condensed metaphysics. It looks more like this machine. Actually, it looks just like your machine. It's the same thing. You have an oven spitting out a beam of, in our case, strontium atoms, of course at 500 meters or so per second velocity. To slow these atoms, we have a counter-propagating laser beam. Every time an atom scatters one of these laser cooling photons, the momentum of the photon is transferred to the atom, and the atom slows down by like half a centimeter per second velocity. If you scatter tens of thousands of photons during the 10 milliseconds that the atoms need flying through the machine, you have here an atomic beam with perhaps 50 meters per second arriving, and using additional laser beams, you cool these atoms even more to millikelvin temperatures, and you also push them to the center of your machine with additional tricks, till you have this little cloud of atoms fluorescing here. That's a magneto-optical trap. You use a few more tricks to cool it down to microkelvins, and then the atoms are cold enough so that you can load them into a so-called optical lattice. It's just an optical dipole trap, a standing wave of light that has this potential landscape for your atoms, and the atoms get just stuck in it like eggs in an egg carton. Now they don't move anymore. So you're ready to interrogate this optical transition by shining a laser beam onto your atoms. If this laser has just the correct frequency, it will excite these atoms, and that's very easy for us to detect. But if the laser has drifted away in frequency, you excite less, and you see that, and you can then, by playing around with the frequency of the laser, determine where you have to push it back to hit the atomic transition. So this laser is then stabilized accurately onto the transition of the atoms, and then, yeah, that's already a clock. But some people don't like their clock to tick at 460 terahertz. Those people then buy an optical frequency comp as a clockwork to translate this high optical frequency into whatever other frequency you want. And that can be, for example, fed to electronics to move the dials, the hands on the dial of a clock. And the best of these optical clocks would go wrong by 1 second over the lifetime of the universe. This is 10 to the minus 18 accuracy. It's really great. You can do a lot of things with it. So, for example, did you see the movie Interstellar? Where astronauts approach a black hole, and the ones which get closer, they age slower. Now, unfortunately, close to Earth, we don't have a black hole, so we can't experience this effect in our life, really. But these clocks are so precise that they can see gravitational time dilation in the weak gravitational field of Earth. For example, already over 10 years ago, our colleagues at NIST in Boulder built 2 clocks, and then they compared the frequency of these clocks. This is the data you see here. And then they forklifted one of these 2 optical clocks up by 33 centimeters and compared the frequency again. And you see the data points are clearly different. And it's just because, gravitational time dilation. Your feet age slower than your head. Or if you're theorists. So if you have a hard problem to crack, you just have to make a handstand. Then your brain goes faster. Yeah. And we can also investigate more fundamental things. For example, are the constants of nature really constant? We don't know. How can we find out? We can build 2 of these optical clocks based on different chemical elements. And then we compare the frequency today. We get just a number. 2 frequencies divided by each other is just a number, and constant of nature. And then we wait a year and measure the frequency ratio again. And if we see a different number, then we probably made a mistake. But if we didn't make a mistake, then we perhaps observed the constants of nature change. And that would be so cool. And of course, we don't know. Is it the electron to proton mass ratio? Is it the fine structure constant? What is it? What changed? We can still find out by building 10 clocks based on molecular transitions and nuclear transitions and different optical, chemical elements and so on. And then we can kind of triangulate what's happening there, what's changing. And there are lots of other applications with network synchronization, navigation, underground exploration, and so forth, geodesy. So this is one use of ultracold atoms. Another important use is to use ultracold atoms for atom interferometry. So you all know LIGO, laser interferometry, where you look at the phase difference that the laser beam picks up when traveling along through paths. You can do the same thing with atoms. You send an atom through a beam splitter, which puts it onto 2 paths, and then we combine these 2 paths again. And independence of the phase difference that the atom picks up along the 2 paths, you get more or less output at the 2 ports of the beam splitter. And atoms do have mass in contrast to photons. So such atom interferometers are super sensitive to gravity and accelerations. And to get them really sensitive, you need to make this free flight time long. You need to make the area here very big. And that only works if you're really cold atoms. If your atoms are kind of standing still, you can just like throw them up on your machine and they make like a fountain. Free flight, and you have all the time available for you to measure it. And that only works if your atoms initially are very, very cold. If you start doing this with a hot cloud of atoms, which moves with like hundreds of meters per second, they will just, when you release them from your track, fly outwards, stick to the walls of the vacuum chamber, nothing works. So ultracold atoms are great for that as well. Now we want to contribute to this research field of ultracold quantum sensing, and we do this in several of our experiments. In one experiment, we want to build a continuous atom laser. We didn't quite go there, but we went quite far. I mean, we have now a Bose-Einstein condensate that lives for as long as we want. And on our way to doing this, we developed a new technique with which we can provide a continuous beam of microkelvin cold strontium atoms in the dark. And it turns out that this beam itself is very useful for other things. For example, you can use it to build a new type of optical clock, a so-called superradiant clock. Now I'm going to explain first our goal of making a continuous atom laser, why we want to do it, then what we achieved, and finally I'll end with the superradiant clock effort. So, what is a laser? A laser is just a wave that describes many particles. It's a beautiful wave, of course. And lasers are great because they have better divergence, brightness, spatial mode structure, and coherence than thermal sources of particles, and they offer potential for squeezing. This is really good for atom interferometry. It's your ultimate source for that. Now, how do we create a laser beam? Let's compare optics and atomics, so to say. In optics, you could just fill one mode of an optical cavity with lots and lots of photons, then make one of the mirrors of the cavity a little bit transparent, and the photons trickle out. That gives you a laser beam. People made an atom laser in exactly the same way. So you take a gas of atom, cool it down by laser cooling and evaporative cooling till you have a Bose-Einstein condensate in the ground state of your trap. And then you make your trap a little bit leaky and the atoms fall out by gravity, and it's still a coherent matter wave that is now falling down. That's an atom laser beam. Unfortunately, such a laser beam doesn't last very long because eventually all the atoms from the BEC have been outcoupled, and that's it, end of story. So in optics, we put an inverted gain medium into the cavity to entertain the lasering process longer. And we do the same. For us, that means putting a thermal gas of atoms around the BEC, and this thermal gas needs to have a very high phase-space density. If it has this, there will be Bose-enhanced elastic collisions driving more atoms into your BEC. Like this, the lasing lasts a little bit longer, but eventually, of course, the inversion of the gain medium or the phase-space density of the thermal gas will be bad and it won't last longer. So you pump. And for us, pumping means continuously supplying the central region here with more thermal atoms and somehow making these atoms be integrated into the thermal cloud around the BEC and keep the thermal cloud at high phase-space density. We can easily do this by laser cooling the thermal gas around the BEC. And by the way, this is not only important because the laser beam here takes atoms away from the BEC. It's so that these BECs are typically very dense. And that means there are three-body collisions and molecules are constantly being formed. And there's a constant loss process that you have going on, and you need to fight against this. Yeah. Okay, now, we didn't completely make an atom laser, but we made a BEC that lasts forever, which is the equivalent of having an optical laser that has this one macroscopic mode always there. Yeah, it's, the only thing missing is that the output mirror isn't half a little bit transparent, so no beams yet coming out. That's what we are working on now. Good. Now a little bit history of atom lasers. Of course, people can make BECs by laser and evaporative cooling since a long time, and they can outcouple atoms from the trap. And here you see a few images of atom lasers that were done over 20 years ago. Of course, these lasers are kind of bad because they stop working after like 100 milliseconds or so if you operate them at a decent flux because the atoms are gone. And that's really bad for precision measurement. Yeah, you can only measure once the laser beam is there, and that's only like 1% of the time. Now, the solution to this is clear. You just need to execute all these cooling stages at the same time, but one after the other in space. Yeah? But that's not so easy because these various cooling stages are not super compatible with each other. All the same, there was a lot of progress over the last years. People have periodically replenished BECs, there was a continuous evaporation experiment, and so on. But they couldn't quite reach continuous Bose-Einstein condensation. And the reason is that they operated their machines with either alkalis or chromium. And these elements just can't be laser cooled very well. And in addition, a BEC is really incompatible with laser cooling. Imagine you have atoms in a BEC, they're essentially standing still. And if there's a little bit of laser cooling light around, an atom might absorb one of these photons and that gives a momentum kick of the photon onto the atom, and this atom flies away with a centimeter per second velocity. That's a thermal atom, it's not a BEC atom anymore. So all this nice laser cooling light that you surely need is really deadly for BECs if you don't pay attention. Now, we work with strontium, and that element allows us new tricks. We have a broad and a narrow laser cooling transition, and we have a trick for making our atoms transparent against the light from the narrow laser cooling transition. So how do we do this? I show you here a precursor experiment that we did in 2012 on our way to an atom laser. In this precursor experiment, we made a BEC that lives inside a thermal cloud that is laser cooled. And we only use laser cooling to create the BEC. So how did this experiment work? It's a pulsed experiment. First, we accumulate atoms by laser cooling on this broad blue transition. Then, and we need to do this because the atoms coming out of the oven are very, very fast. Only a really strong transition can scatter enough photons to slow and stop the atoms. So we start with a blue transition, then we switch over to the kilohertz line with narrow transition. And you have to know that the density you can reach is better if you're working with narrow transition. The temperature is just much lower if it's proportional to the linets of the transition. So you go from millikelvins to microkelvins temperature in no time by switching the transition. And if you do this in an optical dipole trap, your gas also gets quite dense, and then you have already a phase-space density of 0.1. Remember, Einstein told us you need to go above 2.6 to get a BEC. Now, that means we need to get a bit denser, and we can do this by adding a dipole trap. So we shape our potential in this manner. And then the atoms, they can enter this little dimple, as we call it. And the density inside this dimple is increased. It's just like air at ocean level is much denser than air on top of Mount Everest. But the temperature is the same throughout because there are lots of collisions, elastic collisions between the atoms. So in case there is something hotter in the middle, these elastic collisions, they make thermal contact between the center of the cloud and the outside. So the heat is transported from the center to the outside where it can be laser cooled away. And laser cooling is constantly on in this experiment here, and we don't have a BEC yet because the BEC gets destroyed by the laser cooling photon. So we need to somehow protect the central region to get a BEC, and we can do this with a trick. We call it the transparency beam trick. We send yet another laser beam onto the centermost part of our cloud. This laser beam dresses the optically excited state of the laser cooling transition. That it just shifts it away in energy enormously, by 10 megahertz compared, is really big compared to the 7 kilohertz Leibniz transition of the laser cooling transition. So atoms that are exposed to this transparency beam light, they cannot absorb laser cooling photons anymore. And you see it here in this absorption image, which I took using laser cooling light. Yeah, it's just transparent. There's a hole in this cloud, but in reality, there are in as many atoms here than there are here. They just don't get disturbed anymore by the laser cooling light. And if I now look, if we have a BEC, okay, in situ, in these images, which I don't see it, the cloud is too dense, the BEC is too small. So what we typically do, we switch the whole system off, we let the cloud expand and drop, and then take an image. And if I do this, I can see this elliptical shape. And yeah, you have to believe me that BECs, they look elliptical. If I have a thermal cloud, the atoms fly in random directions. If you switch your trap off, they expand in any direction, you get something round. But the BEC, the atoms are very dense and they have interaction energy between each other. And this interaction energy is liberated during this time of flight. And it is liberated first in the dimension in which the BEC is smallest. It's like the atoms roll down their own potential hill, which is steepest in the direction where the cloud is the smallest. And that's, we levitate our atoms against gravity. So our BECs typically look like a pancake. Yeah? So in the radial direction, don't particularly confine them, but vertically we do. And so this pancake, its mean field energy is liberated vertically when we switch the trap off. And that's why our BECs always look like these cigars in the vertical direction. Okay,
In some sense, the shape of the BEC is indirectly telling you what shape the actual BEC
it's an
before you...
Exactly. In fact, the track frequencies, I can calculate everything there. So for my talk, just remember, if you see anything elliptical, it's a BEC. Yes, to summarize, what did we achieve here? We got a BEC sitting inside a thermal cloud that was constantly laser cooled. What's missing to an atom laser? What's missing is continuously replenishing the system with new atoms. The laser cooling is there, that's great, so we can accept these atoms flying in. But we need to provide them. And of course the outcoupling is missing. The outcoupling is still missing, we are working on that. But the replenishing we managed.
Is there also, sorry to interrupt, is there evaporative cooling or not?
Not yet. I hope to implement at this. You know, for evaporative cooling, you have to be in this runaway regime where you have more and more elastic collisions, or at least the same amount of elastic collision while it's going on. And we are not there. We are not at the threshold. We have too few elastic collisions right now to do this. But I have hopes that we can increase the flux of atoms through our system by at least a factor 10 approaching this regime. So perhaps one day we will be able to do it. Okay, so now, what challenge do we have to solve? I told you that the atoms coming out of the oven are really fast, and the only way of cooling them is to use this 30 megahertz Reynolds transition. However, our transparency beam trick, it just doesn't work for this transition. You would have to shift this state too much. You can't do that. We need to protect our BECs somehow differently from this blue light, which we absolutely need. And the obvious solution is to spatially separate this blue laser cooling from the red laser cooling. But that means we need to build a new machine, which looks something like this. The start is the same as I explained before, oven, Siemens law, mod. But then we guide the atoms into a second part of the vacuum chamber where we have very little stray light from this blue transition, and where we can safely make a BEC. So we built a new machine. Started in 2015. We started building, and in like 2019 it started to. 2019 we had the BEC. So often Siemens law is hidden behind here. Here, this is blue mod chamber, sending the atoms downwards here, and here is the red mod. Let's zoom in into this lower part. That's a fancy computer graphics of what happens here. These atoms, they're falling down from the blue mod, from the upper chamber. And then down here, we only use this gentle red light on the kilohertz Reynolds transition. We capture these atoms again in this magneto-optical trap, and then we push them into an optical dipole guide, and actually then once they are safely away from all these relatively bright laser cooling beams, we stop them and fill them gently into this cross dipole trap configuration, which you have seen before. So, in reality, it looks like this. Here's the beam coming in. Here's this turnaround region. We push them into this crossed guide with the crossing beam. Here makes this little enhancement. And again, we don't have phase contrast imaging and high resolution imaging and so on. I mean, your method with holography would be really nice, but we don't have it. So we just switch everything off to see what's going on. And then all this cloud expands. You see here the expanded cloud from the guide and from the turnaround region. And here, this is the expansion from the reservoir and the dimple. And there's nothing elliptic here, so no BEC. Let's see if we can make.
So you said they were falling down. Does that mean that gravity actually plays a role in this?
Oh yeah. Oh, it's super important. Yes. So the gravity accelerates them to 6 meters per second once they come here, and then we have to slow them with a vertically oriented Siemens lower beam down again. So now let's run a few experiments. Our machine is switched off. Then we suddenly switch all the laser beams on, which of course starts atoms flowing through the apertures into this crossed dipole trap. And then after a little while, we switch everything off and make one of these time-of-flight images. So if we just wait 1.1 seconds, we have very few atoms in the reservoir. And then 1.5, yeah, you see this reservoir starts filling, and more, and then, if you go beyond 3 point something seconds, you see an elliptic feature appearing here. And then nothing really changes anymore. So that's interesting. So why does nothing change anymore? It's just that the gas in this dimple is super dense, 10 to the 15 atoms per centimeter cubed, and that means there's chemistry going on. They're just burning away. 3 atoms encounter each other, 2 atoms form a molecule, the third atom flies away to take care of the energy conservation, the momentum conservation. Yeah, and the BEC still nothing decays because we feed all these atoms in all the time. 100,000 atoms per second are newly fed into the dimple all the time. That's why it's constant. Now, we need to prove that this is a BEC. So what do you do if you see this the first time? You fit theory models. And the simplest model we can have, let's assume it's not a BEC. Let's assume it's just a thermal cloud. Then we fit it with 3 Gaussians for a dimple, reservoir, turnaround region, and a tube Gaussian for the influx. And yeah, if you don't have this elliptical feature, it perfectly well describes the data. But here, with this elliptical feature, it just doesn't describe it anymore. So that, and it is just elliptical in the right way to be a BEC. Then we add a Thomas Fermi profile for the BEC, and now the model can fit both types of data. And we also, of course, analyzed when does this feature appear, which density, and so on. And it all makes sense. We can fit that. So we are convinced it's a Bose-Einstein condensate. So that's what we have reached. Continuous Bose-Einstein condensation.
So what is the fraction of atoms in the BEC?
We have 7,500 atoms in the BEC. We have several 100,000 atoms in the dimple, and I think it was 600,000 in the whole reservoir. Yeah. So it's a teeny fraction.
And if I would compute, let's say this uses computation, I'm just curious if I compute the flux of atoms going out the oven, and then the flux of atoms out of the BEC disappearing through free-body radius. What is the...
But the full efficiency, huh?
Yeah.
Okay, I mean, from the oven, I unfortunately don't have a very precise number. But I do know that the transfer from the blue mod to the lower mod is pretty efficient. We don't lose very much there. The bottleneck in our scheme is, funny enough, the loading of this cross-dipole trap, because it's laser-cooled, and there are light shift issues, and there's a dangerous zone where the laser is effectively Bloody-tuned and heats the atoms, through which this whole atomic flux needs to go, and we lose 9 of 10 atoms while doing this. This is just because we use 1064 nanometer light. It's the easiest light to build a dipole trap, and we didn't realize this really. Once we modeled our data, we saw it, and now we are on the way of replacing this dipole trap, which is a much nicer one, which shouldn't have this deadly zone anymore. Perhaps we can increase our flux like this already by a factor of 10. Yeah. Oh, by the way, you are all here. So this is not a thermalized system. Perhaps this is of interest to you. We initially tried to fit our data with just Bose distribution at a fixed temperature. It doesn't work. And the thing is that you have an enormous influx. You drive 100,000 atoms per second into the dimple, and you have 100,000 atoms per second being burned up in 3-body recombination here around the BEC. And these atoms have to somehow dribble down, or, I mean, spatially they have to approach the center, but also energy-wise they have to dribble down here by elastic collisions. And that takes time. And so effectively what happens if you have an overpopulation of the higher energy states compared to a pure Bose distribution with its exponential tail. We didn't perfectly model it, we just made Jeremy made a little model for us, and he just used a mathematical function which has more population in higher states than a Bose distribution. With that, we can model it also the dynamics, what happens when loading and letting the system decay. He just used the Fermi distribution, but it has nothing to do with Fermions.
What is the energy at which the atoms enter predominantly compared to the temperature that you find from the fit? I'm just wondering how.
I mean, the temperature here is about 900 nanokelvin. That's
what
and the depth of the dimple passage set is 3.5 microkelvin roughly. So if you see it, in principle, if you have individual atoms and no collisions, the atoms would roll down this potential hill of the dimple, or as valley rather, and they would get 3.5 microkelvin.
I'm just wondering where, let's say in the steady state, you will say you fit some part of the distribution function with the Bose or with the thermal distribution, and some part.
Yeah, outside it works where the density is not high.
Yeah, so the temperature that you extract, you say, is
from the wings.
Yeah.
Yes, it's 900 nanokelvins in the rest.
And then, like when you draw this arrow of atoms coming in, what is that energy? Let's say.
I think, I mean, yeah, it's 3.5 microkelvin roughly. That's the dimple depth, I would say.
Ah, okay. So sorry, so it's like a factor of 4 higher.
Yeah. I have a question about the chemistry in this dimple. Not the actual chemistry, just about the scaling of the burning, so to speak. So you said that, okay, maybe we get rid of the deadly zone, we have 10 more, a factor of 10 more atoms falling into the dimple, but I'm guessing the burnout is also not linear here, because as they come together.
It's n squared, the density squared. Yeah, one atom has to find another proportional to density, and then the pair has to find another density squared.
So it starts burning even faster.
Yeah. And so how does this come about? So yeah, after Einstein, you have we can reach a certain temperature with laser cooling. It's just given to us, 900 nanokelvin. We can't do much about it. And the critical density at that temperature for the mass of strontium happens to be 10 to the 15 atoms per centimeter cubed, which is really, really quite dense. Yeah, so we would love to have some way of cooling to 100 nanokelvin, and the density would be 10 to the 14, and then, of course, we have the negligible three-body recombination suddenly. Yeah. We will do this one day. I mean, there are new schemes of laser cooling in our heads using clock transition line and Sisyphus cooling, or evaporative cooling. Yeah. But right now we are working on this outcoupling. So we have already, I mean, we need to transfer the atoms into an internal state that's not influenced by the dipole trap. For that we use, a long-lived metastable state instance in the upper clock state actually. We have the transfer of a BEC from the constant to that state. So you have seen we made a continuous BEC, but a crucial part of it was to get this continuous beam of microkelvin called strontium atoms in the dark working. And that beam is very useful for many other things. For example, superradiant clocks. So now I want to explain to you what a superradiant clock is and why it's so special. And for that, I will dive first deeper into the operation scheme of a normal clock. So, in a clock, of course, you also have to first laser cool your atoms on the blue and red transition. You capture them in this magic wavelengths, optical lattice, magic, so it doesn't shift the clock transition around. You interrogate your atoms, that destroys the atoms, and you have to produce a new ensemble. So again, it's a pulse machine, and that's really bad. Lasers are nasty. If you don't tell them to behave and stay on a certain frequency, they will drift away. And the time it takes to interrogate enough atomic ensembles to average your data and know what the laser is doing, it's too late. It's drifted a lot away. So you need to lock your laser while you prepare new atoms onto another reference, and this is just a macroscopic resonance, an ultra-stable resonator, which is pretty complicated to build, actually. It's a whole experiment on its own. Yes, so from the resonator, from its length, you get the short-term stability of the laser, and from the atoms, you get the accuracy and the long-term stability. Now, if you look at the scheme, there are at least two things that you would like to improve immediately. Obviously, you would like to have atoms available all the time to get a feedback signal all the time. And you would really like to not have to build these super duper complicated resonators. I mean, you still need one, but could you do it perhaps like 100 times less expensive? Or, yeah. Okay, and that can be done. And there are two ways of doing it. And one way of doing it is to build a so-called superradiant clock. So it's a so-called active clock. What's active and passive in clocks? in a passive clock, that's what I explained to you so far, you have the atoms and they're just sitting there and passively receive this laser light and get excited, and we look at what happened. They're the victims of the laser, so to say. And in an active clock, we put a continuous stream of microcavern called strontium atoms into the optically excited state of the clock transition and feed them into a cavity. And in this cavity, they decay and put a photon into the cavity mode, and out comes a laser beam on the millihertz line with clock transition directly. So the atoms actively give you photons. Now, this looks like a laser, and it is one, but it's absolutely not a normal laser. So in a normal laser, you use stimulated emission to get your photons. So you have an inverted medium, you have a lot of electromagnetic field in one mode of the cavity, and stimulation gives you more photons. To do that, you need to make your cavity quite good. And that means the cavity itself has a narrow line width. And all these lasers narrower actually than the atomic transition. And that means the frequency of the laser coming out here is given to you mostly by the cavity length. This is a classical frequency reference. And if somehow a temperature change or vibration changes the cavity length, the phase of the outgoing light changes. Yeah? That's bad. Now, in a superradiant laser, that's completely inverted. You choose an atomic transition that's much, much narrower than the cavity line width. And then you somehow, I'll explain later how, make the atoms emit photons on this transition. And the frequency of these photons is given to you by the atomic transition, not by the cavity, because the cavity mode can be 1,000 times broader than the atomic transition, or even 1,000,000 times broader than the atomic transition. And if now the length of the cavity changes, okay, the cavity mode wiggles a little bit around, but it barely changes the phase of the outgoing light. So that's great. This frequency is really given to you by the atomic transition. Now, I said it barely influences it. In reality, you know, you have this gain profile. If the cavity mode wiggles around, you are sitting here with your emission on a different slope of the profile that tilts the effective frequency spectrum of the outgoing light. There's a tiny influence still, it's called cavity pulling. We don't really like that. So you could ask yourself, why can't we make an active clock without this cavity? I mean, it's disturbing us, no? Let's try. Let's just take 100,000 cold strontium atoms, put them all into the upper clock state, and just see if you get photons out of it. And you must, spontaneous emission. The photons will come out eventually. However, it's a clock transition. It has millihertz line width. Fourier transformed, that's 2 minutes. So you get 100,000 photons within 2 minutes, and they are sent out into all of space. So you barely can detect them, and you for sure can't measure their frequency. This is a crappy clock. Yeah, I mean, you can't use it. So you need to somehow enhance the emission of your atoms into a single mode, and that's what the cavity is good for. That's what it's doing for you. You use the effect of superradiance. So how does this work? Here I make 3 Gedanken experiments. The first one is the one I showed you on the previous slide. We have lots and lots of excited atoms, and they just spontaneously decay. All these emitters here, all the phases of these individual emissions of electromagnetic waves are incoherent. So you just have random superposition of these electromagnetic waves, and yeah, the power is just n times the power of a single atom, when n is the atom number. That's not good. That's exactly what I had before. Now imagine you would put your atoms really close to each other. In both cases, the atoms are sitting essentially on top of each other, and you would give them all the same phase. Then the electric fields constructively add up, and the power is, of course, electric field squared. So you get suddenly a much, much faster emission. You have 100,000 atoms. This is a really fast emission now. That's good enough. Yeah, in 100 milliseconds you get all your photons. But you can't technically do this because you can't put all these atoms that close to each other. They would react with each other. So you space them out. For example, here I spaced them out with a spacing of λ/2, which is pretty big spacing. And I actually gave them alternating emission phases. And if I add up all these electric fields, I get this type of pattern. You have two like end-fire modes, yeah? And that looks already pretty much like a cavity field, no? I mean, look at it. If I plot a cavity and a standing wave in a cavity on top of my atoms, you see that the standing wave's electric field, you know, it has opposite phases in neighboring antinodes, just like what I need for my atoms to emit like this. Now let's put it all together. Imagine you have many optically excited atoms in your cavity. At some point, one of these atoms will start emitting a photon. This photon will build up a little electromagnetic field in the cavity. And this electric field, it will torque the Bloch vector, if you know the Bloch vector, it torques it a little bit. So all the other atoms will now suddenly be tickled by this field and be torqued, and then if they're not pointing to the north pole of the Bloch vector anymore, but a little bit to the side, they precess. And that is just in the Bloch vector picture, the emission. It shows you the phase of the emission. And it's now all correct. All these emissions are exactly as they should be. And you don't have to do anything. It will automatically arise just because of the presence of this cavity. And you don't need a strong electric field, as you would need for stimulated emission. A teeny tiny field to tickle your atoms, to torque your Bloch vectors is enough. And of course, it's a collective effect. It's not that one atom starts decaying. And then all these atoms radiate together. It's a phased array antenna. And the photons will go to the cavity, but remember, it's a bad cavity. It leaks very, very much, so the photons quickly go out, and at some point all the atoms have decayed, and there are no photons left anymore. And that's it. So you get one pulse of superradiant light out. And that has been shown by James Thomson and Schiller in 2016 on this Johnson clock transition. But one pulse, I mean, Fourier transform it, it's 10 hertz wide. You can't measure the frequency very well. You want millihertz line widths. You want to observe this for 2 minutes. So you need to entertain this continuously. And the basic principle of this is super easy. You just push a continuous beam of strontium atoms all in the upper clock states through the cavity. And once an atom enters a cavity, it gets torqued by the tiny electric field just in the right way, synchronizes up with the existing ensemble, decays, puts its energy, its photon into the cavity mode while it flies through, and then when it's flying out, it's mostly decayed. Yeah. So that's what we want. By the way, you can see that a condition for making this work is you should not move along the cavity direction, because if an atom enters, say here, it synchronizes up with this phase. If it would fly diagonally like this, it would sit in the opposite antinode, and it would be just the wrong phase, and it would suck energy out of the cavity. It's really bad. This is a condition which we as experimentalists need to satisfy, which is hard. And you need also a critical flux of atoms through it, which is also hard. And because it's so hard, we built two machines. So the first machine is not having the ambition of operating on the millihertz transition, but it operates on the kilohertz transition. And that can actually be done with a hot thermal beam, which is just slightly transversely cool. And yeah, so here, oven, cooling, optical pumping with the right state, cavity up here. And we currently have a gain of 10%. So if you seed your cavity with a teeny tiny bit of light, it's amplified by our inverted medium. And we need to just crank it up a little bit. 10 times more atoms and we would be there, or a little bit higher finesse and we would be there. And then we also build a second machine really with goal of millihertz superradiance, often Siemens law, blue mode, red mode. You see, that's the same structure as the atom laser machine. But atom laser machine that is 3.5 meters long, this is 1.2 meters long. And we could do this because we learned so much. Yeah, in the meantime. And here's in the cavity where we will make it work. Okay. So.
Welcome to the technical classes. Today I'll show you a little bit what we have around us. So we are still building bases, so it's a little bit of a mess, but not super fun. So let me start from our machine. We are building a QuMat clock. So you don't see it from here, but the atoms are starting from an oven that is like below there. And they then travel vertically, and we use blue and red light, and the blue you can see, to manipulate them. and prepare them for the final stage that is in a cavity that is more or less at this height, where they then are going to separately emit, and this is the signal we are interested in. Now we use different optics, so you can put here distribution systems, different distribution systems to prepare the lights we need, and we control the different stages thanks to software. So that here it's in particular the one related to our experiment, and we also monitor the different lasers using cameras, and I'll show you where the lasers are. So first we arrive to the electronics cabinet. So here we have the different RF amplifiers and frequency generators to control again the frequency of lasers and prepare them. And the real object right here. So we have blue and red. And okay. Yeah, thank you for this short introduction. I can show you other people working here. So perhaps we have Camila. And our Stefan and Shannon, and the other. So yeah, thank you for this very short tour. And
Yeah, thank you, Francesca. So that was it. That was what I wanted to tell you about. Yeah, we made a BEC that it lasts for as long as we want. We have the ambition of making a continuous atom laser out of it, which would be really good for atom interferometry. We also have this continuous microcoherent beam, which is also already great for atom interferometry. Perhaps we will build a gyroscope, which is with it one day. Currently, we are trying to build superradiant clocks. And yeah, we have two parts in our group. One is quantum sensing, that was what I was talking about today. We also have a quantum simulation part. So we have the ambition of making rubidium-strontium molecules and use them for quantum simulation and quantum chemistry. We have an experiment where we have single strontium atoms in areas of optical fields. You know that very well. And we are just starting Sierpinski triangles for you guys. Yeah. And we do also have a new project within quantum delta and L, and there the goal is, you have seen the labs, they're really complicated and big. And these clocks, they could be very useful for geodesists, for network synchronization, for all kinds of things, but if you can't pay 2-3 million euros per clock, wait 3 years for it to be delivered, and with 2 PhD students, which you have to hire to operate it. I mean, nobody would do this. So you need to make it much more compact and reliable and push button. And the Achilles heel of these systems are really the laser systems. So we are working hard on making those much more reliable and compact. And we also want to provide easy access to the system. We work on simple operating schemes. And yeah, we do this within quantum delta and L. And with the Quantum Flagship project Acura, we built an industry clock. We built a clock that will be the time and frequency reference of the Netherlands, also in collaboration with the Dutch Metrology Institute, and we will provide access to these signals through telecom fibers. Yeah, I mean, I could talk a lot more. That's pretty cool. We built a zero daytime clock based on our continuous scheme. And of course, I mean, many people to work on these things, and here are the heroes of this story. Thank you.
What is the killer application for
Gravitational wave detection for me, but if you ask other people, it's navigation. So if you have a submarine and you want to have it under the ocean so that nobody knows where it is, And under the ocean, you don't have GPS signals because of the salt in the water. So you can use inertial navigation, but with classical sensors, the sensors drift with temperature and everything. They have an offset, and if you integrate this acceleration from the classical sensors, you quickly lose the position. But if you could reference yourself to ultra-cold atom sensors, on the long time scales, you could integrate up for a long time. I mean, you want to integrate up for weeks. Yeah, okay. I hope it also has a civilian application one day. And then, yeah.
Okay. No, that's clear. It's, yeah.
I'm deferring to the chair. Are there any other questions?
I have one, but it's related with, I don't know if maybe there is a relation with Hawking mechanism, maybe with the Hawking radiation. Because, well, in like an analog of black hole, maybe, because when you show the Bose-Einstein condensate that they like linked atoms, right? There's a creation of a hole, but I don't know if it's possible to measure like a radiance photons of these density.
There are a few people in the world pursuing this. Is Jeff Steiner in Israel, I think, who published something recent, a few years back on it. Yeah, so you need, of course, a big BEC and make an enormous outflux by purpose, and then somehow get hints in this Hawking radiation. I mean, this is super weak. So what they somehow did, they put it essentially into a resonator and see it amplify itself somehow. You can find this out.
But you can reproduce the same.
Yeah, but at least currently our BECs in a nasty environment. It's in this dense downward cloud. We could never hope to see a subtle effect like Hawking radiation.
We had a lot of questions already during the talk, so I think this is a good time to thank our speaker.
Yeah, thanks.